morning Alexander Efimov with the Logarithmic Hochschild complex. Thank you.
Thank you. I'd like to thank the organizers for the invitation to this conference. So I will be talking about logarithmic Hochschild complex. It's actually not an ideal result, so it's some intermediate some intermediate construction which should be somehow made. Should be simplified ideally. But so far, I will present the construction of the logarithmic Hochschild complex, which will correspond to the logarithmic Rham complex. But first, using some heavy machinery like K-theory. First, I just recall the usual Hochschild-Rosenberg theorem. If A is the G algebra, then its Hochschild homology is just the product of the diagonal bimodal with itself. It's defined for any algebra, and if you replace one of the factors by the reduced power dilution, you get the standard chain Hochschild complex. Well, I'm taking reduced one; it's just more convenient. So it's made up of tensor powers of A, the appropriate shift, and the differential has two components. As usually, one of them is just corresponds to the is just given by the differential on A. So it's just a standard differential of tensor powers, and another one is given by the multiplication in A. And it's just taking products of two consequent factors, but we also fix one of them, and we also take the product of the last one with the first one. So it's standard formula for the differential, and there is a well-known now classical result by Hochschild, Constant, and Rosenberg, which states that if A is finitely generated commutative K algebra, which is just an algebra of functions on a smooth affine variety, then this Hochschild homology is identified with differential forms on this affine variety. And moreover, you can give it by this isomorphism by explicit formula. Here I'm restricting to the characteristic zero case. I just don't want at the moment to discuss the characteristic issues. This isomorphism is given by just a zero tensor and so on. An goes to 1 over n factorial of this corresponding differential form. The surprising discovery made by Kohn and Sigan independently is that the Rham differential on this classical differential forms on affine variety corresponds to a completely general additional differential on the Hochschild complex, and for this reduced Hochschild complex, it's given as follows. We just take all the cyclic permutations of our element of tensor power and just attach the unit on the left. With appropriate signs, of course. It can be checked, of course, if you write down the signs. Then both differentials square to zero and anti-commute with each other, and they have opposite cohomological degrees. So the quotient differential is of course of degree 1, and this consignant differential is of degree -1. So this triple is what's called a mixed complex. And I just recall that a morphism of mixed complexes is said to be a quasi-isomorphism if the underlying morphism of complexes is a quasi-isomorphism if you just forget this additional differential. So in other words, this mixed complexes can be described also as DG models of a two-dimensional DG algebra. which is generated by an element of degree -1, which squares to 0 and which is closed. Yeah, so this is all. So far, this is all standard. So it's just the usual Hochschild homology, and all the constructions are entirely k-linear. So it just takes an algebra and produces some complex using its tensor powers and the operations in this algebras. Yes, and this Hochschild constant Rosenberg map, which was mentioned above, gives actually a quasi-isomorphism of this mixed complexes, where we have this Hochschild mixed complex, and we make the differential, the Rham complex into a mixed complex in a bit strange way. So we put n forms to degree -n, define what corresponds to Hochschild differential is just 0, and what corresponds to constituent differential is just the Rham differential. And the Hochschild constant of Rosenberg is compatible with both of the differentials, and we already mentioned that it is a quasi-isomorphism. This result also generalizes to a non-affine case. So first, the Hochschild homology and the Hochschild complex can be naturally defined for any small dg category. So we still have a diagonal bimodal, and we still have a bar resolution, and the complex is the resulting complex is actually functorial under dg functors. And it also respects Morita equivalences, so it sends Morita equivalence to quasi-isomorphisms. In particular, you can pick two different generators in GG category, and the Hochschild complexes, mixed complexes, will be canonically quasi-isomorphic. I didn't say that, but of course, con differential is defined by the same formula for any DG category. All the triangulated categories which I will be considered are assumed to be DG, and we even basically identify them, so we just don't. This method statement is not quite true. I will need some more, but let's say all the triangulated categories which are related to geometry directly, they will be DG. I shouldn't have written this, because I mean this is wrong statement, but at least any category associated with algebraic variety will be DG. And we use the notation perf of X for the category of perfect complexes. These are complexes which are locally quasi-isomorphic to finite complexes of locally free shifts of finite rank. And and one can use any of the standard enhancements which are all equivalent, for example, by taking resolutions by injective quasi-coherent shifts. So there's a result of Keller, which is a generalization of Hochschild constant Rosenberg to the non-affine case, which states that if you take the mixed complex associated with the DG category of perfect complexes, you will get just R gamma of the mixed complex, which we already considered before. So we just take the sheaf of mixed complexes, and it's clear that you can define R gamma for them and push forwards and pullbacks. So in particular, we have R gamma, and so we have such an identification. Okay, this was all about classical about usual Rham complex and about usual Hochschild homology. And we will be interested in the logarithmic version of this result. So first, I just recall some general facts about logarithmic Rham complex. So if y is a smooth variety over k, and we have some divisor with simple normal crossings, then as already it was defined by Victor Pelkowski yesterday, there are shifts of logarithmic differential forms, and they're defined as follows. The sections of the shifts are just rational differential forms on y, regular outside D, such that both this form and its de Rham differential have poles of order at most 1 along the components of the divisor. Yeah, and we immediately see from the definition that we have a sheaf of DG algebras, which contains the usual regular differential forms, and locally as a graded algebra it is generated over the structure sheaf by the usual one forms and by the forms of the form d logarithm of f, where f has singularities only along d. So f has zeros only along d and is non-vanishing outside d. Yeah, and it is quite easy to check that all of the sheaves are locally free, and essentially, actually, n forms, logarithmic n forms, is just this is just the wedge nth power of the logarithmic one forms. Yeah, so this is standard, and there's a weight filtration on this on the sheaves of log de Rham forms. So it's just given by the number of divisors for which have a pole along along this divisor. So in particular, W0 is just the usual complex of differential forms on Y. Yeah, let us use the following notation. So if we have some subset of divisors, some subset J, then dj is the intersection of these divisors, and if J is empty, then this is just the whole Y. Then the graded quotients of this filtration are given by the shifted direct sums of shifted de Rham complexes on these intersections. So yeah, and so the projections, corresponding projections, are given by the residues. Yeah, now we let us now assume that our ambient variety is proper, and the complement of the divisor is denoted by x. Then the following statements were proved by Rham. So first, the filtered complex. So if you take this R gamma of this logarithmic de Rham complex with this stupid filtration, so you have induced filtration on R gamma. So this invariant depends only on x. It doesn't depend on the choice of a complexification. Yeah. Second, this complex actually computes the de Rham homology of x. So it's not only over complex numbers, but just over any field of characteristic zero. And third, the spectral sequence associated with this filtration degenerates. So it's a generalization of the Cauchy de Rham degeneration for smooth and proper varieties. Yeah, of course, there's a version of this story for logarithmic schemes, but I'm just considering the case only when the log structure is given by a simple normal crossing divider. And the scheme, the underlying scheme is smooth. Yeah, okay. So we can now define, well, let's just define by force logarithmic Hochschild complex of a variety, but by the same formula as before, but with the usual forms replaced by logarithmic forms. And it just formally follows from the Rham's result that this invariant also depends only on x. So it doesn't depend on the choice of y, on the choice of complexification. Yeah, well, it's just more, just literally formal implication, because I mean this category of mixed complexes can be obtained as an ordered category of filtered complexes of filtered vector spaces. Yeah. So yeah. So as I said, it follows from the first result in this list that that this is an invariant of X, and we want to make it naturally into an invariant of the DG category of perfect complexes on X, so that hopefully it can be applied to an arbitrary DG category, or at least to a smooth DG category. Well, we will not achieve this goal well in full generality, but I will explain the partial result, which gives quite satisfactory picture for the geometric case. So first, I will now switch to some abstract stuff about DG categories and E-theory. So first, one can show it's really not hard to do that if we have a functor between DG categories, then the induced morphism of mixed complexes it depends only on the class of this functor in K0 of functors. Of course, I'm considering functors in the correct form, so this is subcategory in bimodels. So of course, it's not naive DG functors, but the correct version. So it depends on the class in K0, and so we can actually replace when talking about mixed Hochschild complex, we can actually replace the DG categories of functors, but by the K theory. And there is a category which is defined as follows. So its objects are just small DG categories, and the morphisms between them are just given by the spectra, by the K theory spectra of the DG category of functors. Well, I will not, of course, recall what this exactly.
Theoretic spectra.
Yes. So yeah, but just how to think about it, it can be just sort of well, it is not too different from. I mean, the categories enriched over spectra, they're not too different from DG categories. So the point is that the base now is not the ring of integers, but the sphere spectrum, whatever it means. But a lot of things just I mean can be repeated directly from DG categories to categories enriched over spectrum. I just will not explain the technical details here. Yeah. So now the morphisms in this category are given by K theory of the usual categories of functors. Yeah. And here I just recall that any DG category can be considered as a category enriched over spectra. So it is linear over the Algebraic line spectrum of the field. So I mean the world of DG categories embeds into the world of categories enriched over spectra over some base ring spectrum. Yeah, and now we have a spectral functor. So this is actually a refinement of the previous statement. So I said that the morphism on Hochschild complexes depends on the class in K0, but actually the whole spectrum of K theory is acting here, and we have a functor from this universal category to mixed complexes. Let us also consider the full subcategory, which we'll be interested in, of geometric categories, which are just given by perfect complexes on a smooth variety T. And this category was also studied by Gartusha and Panin, and they called it just K motifs. Yeah, and
Do you know about this one?
Mm-hmm.
Okay, thank you.
Yeah, they were not interested in general categories. They were considering just varieties, smooth varieties, and yeah. Okay, now I just recall the abstract notion of smoothness and properness for DG categories. So the DG category is smooth if the diagonal bimodel is perfect, and it is proper if the complexes of morphisms have finite dimensional total homology, so, which means that they're perfect over the base field. And theorem of Lutz and Schnurrer, I think that they were the first who have written this in a paper. So it was known to specialists for some time, and so the scheme X of finite type is smooth and respectively proper if and only if the corresponding DG category of perfect complexes is smooth or proper. Let us consider. Let us just define the non-commutative K motifs to be the full subcategory in this universal category, which consists of smooth and proper DG categories, and inside it we have a subcategory of geometric DG categories where the objects are just perfect complexes on smooth and proper varieties. So we have commutative diagram of these inclusions, and we will be actually interested. I will say something non-trivial only about the essentially about the inclusion on the left. So because in the geometric case there is the K-theory machinery is developed well enough in order to obtain some non-trivial results. For the arrow, for the vertical arrow on the right, hopefully some similar results should hold, but it's conjectural, and I explain what is the difficulty here. In particular, at the moment, the results which I will going to explain are not working for K categories, for example. They're working only in the algebraic geometry situation. Here geom stands for algebraic geometry. For respectable category, we can consider actually it will be a collinear DG category, functors from of spectral functors from S to mixed complexes over K. Now we have just naturally we have a restriction of scalars functors from functors from this the whole world of DG categories to mixed complexes to functors from only smooth and proper. Well, not the whole world. I mean, here I'm just already restricting to smooth but not proper varieties, and we restrict to smooth and proper. So it's just a natural restriction functor of composition with the inclusion, and it has a left joint by the general theory because this category of mixed complexes is complete. So just we have a left joint. And the main result is that the logarithmic Hochschild complex, which I defined by force above, is given by such a composition. So we first take the functor of Hochschild complexes on this geometric non-proper DG categories, restrict it to smooth and proper, and then take the left joint to the restriction. So in particular. Even without proving this theorem, you immediately see that there's an adjunction map from this from the right hand side to the usual Hochschild complex.
In practice, to compute in y.
In practice, yes.
In practice, yes.
But here, it just the definition doesn't use any y. It's just the method. Just the method. It will be the method of computation, but it's defined without any choice of computation. So now I explain why it's true. Just for simplicity, consider the simplest possible case when there is only one divisor at infinity, only one smooth divisor, so no intersections. Let us denote by iota this inclusion of smooth and proper geometric DG categories to all geometric DG categories, and just by the general construction of this left joint, we have an isomorphism. We need to take homes from smooth and proper, from all smooth and proper geometric DG categories to our category curve of X, and tensor it over this non-commutative K motifs, geometric K motifs, with the Hochschild complex. So the Hochschild complex is considered somehow as a left model of this category with values in mixed complexes, and this left factor is a right model. So we just need to take the product of left and right models. And in order to compute this tensor product, we want to have a resolution of at least one of them. And it's clear that one should not try to construct a resolution of the right guy, but of course we construct a resolution of the second, of the left vector. And it has actually a very simple resolution, just of actually of length 1. So if for any smooth and proper geometric category, let us denote by HC the right model represented by itself, the standard notation. And then proposition is that we have an isomorphism. So this functor, so K-theory functors from something smooth and proper to X, to perfect complexes on X. It's just the cone of the push forward between these two representable functors, representable by perfect complexes on D and on Y. So how do we obtain that?
The inclusion is D or Y or X?
No, it's Y.
Oh, Y, I'm sorry. Yes, it's just it's Y. So how do I obtain that? So let Z be any smooth and proper variety over K, and denote by C the category of perfect complexes on it. So smooth and proper category. And then it actually has a property what's called dualizable category. So functors from the C to any DG category is the same as to any, I mean any preterambulated carbon complete. So it's the same as perfect complexes over C opposite tensor T.
So that T should be categorical.
Yes, it should be categorical. In particular, it follows that we have a short exact sequence of DG categories. So functors from C to perfect complexes supported on D, then functors from C to perfect complexes on Y, and functors from C to perfect complexes on the complement. So if C would not be smooth and proper, then we would not, the sequence would not be short exact. So it's important that taking functor from C is the same as multiplying by C opposite, and multiplying by anything is an exact functor. So in this sense, any category is flat, but not projective.
Presumably, when C is not smooth and proper, then the first identification doesn't work.
Yeah, that's what I'm saying. The first identification wouldn't work, so we will not have this short exact sequence. Yeah, now to a short exact sequence of DG categories, we can apply the K-series spectrum and get an exact triangle of spectrum. So we'll get homes from C to this category supported on D. Then it will be already the value of representable functor by perfect complexes on Y, the value on C. And then we have this functor which we are interested in constructing the resolution. So we already started to construct the resolution, but we have one more term which is not representable. Which is not immediately representable, but it turns out that it is actually by the theorem of Wheeler. The geometric application of this Wheeler's Devisage theorem is the following. So if U is any Noetherian scheme and V a closed subscheme, then K-theory of the derived category of V is identified by the push-forward functor with K-theory of derived category supported on V. So these are completely different categories, but their K-theories are identified. Then we just have a chain of isomorphisms. So the functors from C to this category with support. This is the same, just by Fourier-Mackay theory, it's the same as K-theory of perfect complexes supported at Z cross D, over Z cross Y. So it's perfect complexes over Z cross Y. And again, it's because everything is smooth, it is the same as K-theory of DB Koch, supported at Z cross T over Z cross Y. And by Wheeler's Devisage, so here we apply this Wheeler's Devisage, it is the same as K-theory of just coherent shifts on Z cross D. And again by Fourier-Mackay, this is just the value of the representable functor by perfect complexes on T on C. And so what we get is just the exact triangle where we have two representable functors, take their value on C, and so their cone is exactly this homes from C to perfect complexes on X. So this proves the proposition. Now we needed this projective resolution to compute this induction restriction, and just immediately we obtained that this induction restriction is identified with the cone of the usual Hochschild complexes of D and Y. So the cone of homomorphism given by push forward functor. And it follows from the HKR theorem and from the what I explained about the weight filtration that this cone is exactly the log Rham is exactly the logarithmic Hochschild complex, which was defined above by force by taking RGM of log Rham forms. To be more precise, what I explained so far is that this cone and the logarithmic Hochschild complex both have filtrations with the same quotients, but you can actually prove that they are identified by themselves. So this is how it works in the case of a single smooth divisor at infinity. In the general case, when D is not smooth, it is more or less clear that we get a resolution, of course, not of length 1, but it will be a resolution where the length is just the maximum number of divisors with non-empty intersection, and so it will be given by this by the representable, the direct sums of representable functors by the perfect complexes of these intersections. And again, when we compute this induction restriction using this resolution, we will get a similar bicomplex consisting of direct sums of Hochschild complexes of these intersections. And again, by the same analysis of the base filtration, one can check that we will get exactly the logarithmic Hochschild complexes. It's not immediately obvious, by the way. You need to be precise in order to identify it, because so far in this talk I'm only explaining why they have the same. They both have filtrations with the same quotients. But this can be done. So now there are several drawbacks of this construction. We use K-theory we use K-theory spectra to construct an invariant which is K-linear, which ideally, of course, should be just like the Hochschild complex, should be given by some complex of constructed from the G algebra. Possibly it's a bit naive goal, but still. Of course, it looks really strange when you obtain some complex of vector spaces, which is, and to construct it, you are using K-theory, which is highly non-trivial machinery. So the second, which I already mentioned, is that we used the visage to prove the main result, and the equivalence proof it's really based on the fact that the categories under consideration have a T structure. He of course deals in his paper only with abelian categories, but anyway, at least to apply the visage, you need some T structures on your triangulated categories, and of course, not every category that means T structure. For example, it would, it immediately implies vanishing of negative K-theory. So it's not always the case, so again we cannot apply this to the Foucault categories, for example, and it is not even known whether we will obtain the same invariance, if in the construction we replace geometric non-commutative k-motives by the whole non-commutative k-motives, so taking smooth and proper categories which are not geometric, because I mean, well, essentially the problem is here, instead of taking this, well, if my C is not geometric, then what I will need is that when I tensor the so I have the devisage for perfect complexes supported on D on Y. Yeah, and what I want to do is to tensor everything by C and claim that I again have an isomorphism in K theory, and I cannot do it for smooth and proper G categories which are not geometric. So no, I don't have a counterexample, and I'm sure it's actually should be true, but I mean there's no technique available to prove it. Yeah. So yeah, but at least it's not known at the moment whether we will get the same. Yeah. So these are some serious drawbacks of the construction, but still we obtained the Logarithmic Hochschild complex using only the DG categories. So without any choice of computification and so on. Now I will explain that we can obtain not only the Hochschild complex, but well, first we can well, almost for free get a generation of the logarithmic Hochschild Rham spectral sequence if we know it for smooth and proper varieties. So first, the Hochschild Rham generation in the usual case of smooth and proper varieties, it can be reformulated as follows: that we have this mixed Hochschild complex, and that it should be quite isomorphic to the same complex with zero extra differential, which is just a reformulation of the generation of the spectral sequence. And in the case of complex numbers, we have actually more. We have the Hodge theory, which gives us a canonical splitting of the filtration, which in terms of these mixed complexes, it gives a way to decompose the functor of Hochschild complex through the category of complexes of vector spaces, where the second functor here is just when we take this extra differential to be zero. So we can there is such a decomposition, and once we have such a decomposition, it immediately follows from the construction that well, it should be C logarithmic over here. It immediately follows that that the logarithmic Hochschild complex functor here also factors through the complexes of vector spaces, so that the additional differential can be made to be zero. So if you wish, this circle action can be trivialized naturally. Okay. Yeah. So this is just the way to get logarithmic generation for free. Probably even the proof of the link can be somehow, I mean, can be somehow interpreted so that this argument will almost repeat the link's argument. Yeah, but again, this argument is purely categorical, so we need just the categorical construction. Yeah, and then I'd like to explain how to get weight structure on this logarithmic Hochschild complex. So yeah, first I recalled the notion of Misha Bandarko of weight structure on a triangulated category. At least, well, in the case when the triangulated category is enhanced, at least over spectra. Yeah. So if you have such a triangulated category, let's assume for the basis that it's currently complete. We can always construct the truncated category. Just take the morphisms. Well, just at the moment, let's assume that it is just a DG category, not spectral, but just DG. then we can take canonical truncations of the morphisms of complexes to get homologically to get a DG category with the same objects, but the homes are homologically non-positive. The home complexes. So then we have a natural functor from this truncated category of T to T itself, and so we have a functor from the perfect complexes over this truncated category to T. And a bounded weight structure on T is given by choosing a set of generators of T such that homes between them are homologically non-positive. So that homes between them are the same both in T and in the truncated category. And more or less equivalently, we get a fully faithful section from T to these perfect complexes over the truncated category. And also an easy pleasant computation shows that if you apply this construction to just fine-dimensional vector spaces, then you get filtered fine-dimensional vector spaces. This is just a direct computation. Now we finally explain how to get categorical the weight filtration on the logarithmic Hochschild complex. And here we ignore the mixed complex structure, so just on the vector space. Yeah. The structure of a mixed complex. By the proof of the main theorem, it was the formulation of this main theorem. We were taking this induction restriction, but actually it follows from the proof that this logarithmic Hochschild complex functor factors into a composition. So if we first go to perfect complexes over non-commutative geometric K-motifs, because as you remember, we were constructing just finite resolutions of the corresponding functors. And then we go to perfect complexes over K. Now, for any category with a bounded weight structure, not structures but structure, any functor from T to perfect complexes over K, it can be naturally factored through filtered vector spaces. It just follows from this general definition, because we have a section from T to perfect complexes over truncation, then truncation of T goes to truncation of perfect complexes, and then we go back. So it's just immediate implication of the definition that just given any functor, its image comes equipped with the filtration naturally in a functorial way. And now it just remains to note that this category of non-commutative geometric K-motifs has a natural bounded weight structure, which is given by the smooth and proper geometric categories by themselves. And this condition, on this on this set, just vanishing of positive homology, it is satisfied because this positive homology is, in this case, is just negative K theory, and abelian categories don't have negative K theory, so we get a weight structure. And so the functor of logarithmic Hochschild complex naturally factors through filtered perfect complexes. And again, it's more or less clear from the proof that the resulting filtration is exactly the usual weight filtration. So I think I was too fast.
There are questions for our speaker.
So this last thing about weight structure is exactly what Van Dark used, right?
You mean his original motivation?
Yeah.
I think more or less yes, but yeah. But he didn't consider this. But this was his original motivation to interpret the weight filtration conceptually in the categorical way.
Okay, more questions? No? That's a knowledge for speaker. Thank you.
Хорошо, добре, спрятусь.